Ever wondered what makes tree interviews both tricky and fun? Lowest common ancestor of a binary search tree is a Pattern Mastery 100 favorite, routinely used by Google, Facebook, and Amazon to test how well you exploit BST properties. More than 30% of candidates overcomplicate it or miss the power of BST traversal. Let's make sure you're not one of them. Let's solve lowest common ancestor of a BST using the basic framework, a stepwise guide that ensures you never miss an optimization or edge case. Now let's break this down. You're given the root of a binary search tree, BST, and two nodes, P and Q. Your task? Find their lowest common ancestor, LCA, the deepest node in the tree that has both P and Q as descendants. Input: root node of a BST, and two node references P and Q. Output: the node representing their lowest common ancestor. Here is a real-world example. Imagine managing folder permissions in a company's shared drive. To find the closest shared folder for two users' files, you need the LCA. Or, in a genealogy tree, to find the nearest shared ancestor between two people. Let's assess it. What's tricky? With a normal binary tree, you'd need to search both subtrees recursively. But in a BST, every node's left children are smaller, and right children are larger, so you can leverage value comparisons to avoid unnecessary work. Now let's think step by step. Start at the root. If both P and Q are less than root, both nodes are in the left subtree, go left. If both P and Q are greater than root, both nodes are in the right subtree, go right. Otherwise, root is between P and Q, or equals one of them, that's the split point, and the LCA. Let's clarify. You don't need to visit every node. BST ordering lets you home in on the ancestor in OH time, where H is tree height. Edge cases. One node is ancestor of the other. Nodes are on different sides of root. Root is LCA. Here is the structure. Start at root. While root is not null, if both P and Q are less than root, go left. If both are greater than root, go right. Else, root is the LCA, return it. If root becomes null, shouldn't happen for valid input, return null. Now let's implement the BST property approach, walking down the tree and using value comparisons to stop exactly where the paths to both nodes diverge. Main method: we iterate down the tree starting from the root. Because this is a BST, we can use value comparisons to guide us, no need for full traversal. Case 1. Both nodes are in the left subtree. If both target values are less than the current node's value, that means they must lie somewhere in the left subtree. So we move left and continue the search. Case 2. Both nodes are in the right subtree. Similarly, if both values are greater than the current node's value, they must lie in the right subtree. So we move right. Case 3. We found the split point. This is the key moment of the algorithm. If neither of the previous conditions is true, it means we've reached the split point. One target lies on the left, and the other lies on the right, or one of them matches the current node. Either way, this node is the lowest common ancestor. Final fallback: if the root somehow becomes null during traversal, which is rare for valid input, we return null to indicate no LCA was found. And that's how this algorithm works. It first walks down the tree using BST ordering rules, then identifies the exact point where the search paths for both nodes diverge. Efficient, simple, and elegant. Let's test our LCA function with this BST. We're looking for the lowest common ancestor of nodes 2 and 8. In a BST, if one value is smaller than the root and the other is larger, the root is their LCA. Here, 2 is left of 6 and 8 is right of 6, so the split happens exactly at 6. And that's exactly what our program outputs, 6, matching the expected result. So, our implementation is correct. It identifies the correct ancestor using the BST property. Now let's implement the path-based method, first recording the path from the root to each node and then comparing those paths to locate the last common node. We start by computing the path from the root to node P and the path from the root to node Q. Because this is a BST, following each path is efficient, we compare values as we go. We initialize a variable to store the lowest common ancestor. We'll update it as long as both paths share the same nodes in the same order. We iterate through both paths in parallel, stopping at the shorter path's length. This lets us compare nodes level by level. While the two paths still match at index I, we update LK, meaning this node is still a shared ancestor. Once the paths differ, the common ancestry ends. The last matching node is the true LCA. So we break out. We return the last shared node as the lowest common ancestor. This helper builds a list of nodes from the root down to the target value T. We create a list to store the path as we descend. We traverse downward until we reach the target or fall off the tree. We add each visited node to the path list. This single line uses the BST property to decide our direction. If target value is smaller, go left. If target value is larger, go right. If equal, we've reached the target and set R to null to stop the loop efficient and clean. We return the full path from the root to the target node. And that's how this algorithm works. It first traces the root to node paths for both targets, then compares those paths to find the last shared ancestor. Efficient, simple, and elegant. Let's test the LCA function on this simple BST. We want the lowest common ancestor of nodes 2 and 1. The root is 2, and 1 lies directly in its left subtree. Since one of the nodes is the root, the LCA is simply the root itself. And that's exactly what our program outputs, 2, matching the expected answer. So, our implementation is correct. The function handles this small BST perfectly. If BST questions ever felt abstract, this one makes them click. The lowest common ancestor of a BST shows how a tiny ordering rule can guide you straight to the answer without searching everything. Let's do a recap. We're given a BST plus 2 nodes, P and Q. The goal is to return the lowest common ancestor, the deepest node that has both P and Q in its subtree. In plain terms, the closest shared parent in a value-ordered tree. The key advantage is the BST property. Left subtree values are smaller, right subtree values are larger. Instead of exploring both sides like a general tree, we compare P and Q against the current node's value to decide which single direction to go, or to stop at the exact split point. Start at root and loop, or recurse, with 3 simple checks. If P and Q are both smaller than the current node, go left. If both are larger, go right. Otherwise, you've hit the split, or matched one of the nodes, and that current node is the LCA. We followed that plan directly, using straightforward comparisons at each step. No extra data structures, no exhaustive search, just clean movement left or right until the split point appears. We ran it on LeetCode and verified the logic. When P and Q sit on opposite sides, the root at the split is returned. When one is an ancestor of the other, that ancestor is the answer. Edge cases like the root being one of the targets and tiny trees behaved exactly as expected, and everything executed without errors. The takeaway, in a BST, order is a compass. Let value comparisons guide your traversal, and the LCA reveals itself in OH time. No backtracking, no fuss.